Okay. Hi guys, welcome to the Introduction to Akka workshop. The point of this presentation is to give you guys somewhat of an introduction to the basics of Akka and what it's like to develop an application in Akka. We're only going to go through the basics of Akka, so we're not going to delve too deep into the sometimes rather complex matter that Akka has to offer us. So yeah, things should be relatively easy to understand. If people are interested, we can organize a second session in which we will delve more deeply into the more complex parts of Akka. So something about me. I'm Yannick De Turck. I'm a Java developer at Ordina, Belgium, for the guys that are watching our stream. You can find me on Twitter or GitHub. The presentation and the demos that I will be demonstrating will be available on GitHub, so you can find it on my GitHub right there. So, first question: what is Akka exactly? To start off, Akka is a toolkit and not a framework. And what we mean with that is that you can simply add Akka to an existing project. And unlike a framework, you don't really have to follow a particular source code layout in order to fully utilize the framework. So you just add the dependency in your Maven project or in SBT, and then you're good to go to start using Akka in your application. Akka has been founded by Jonas Bonner and is part of the reactive platform stack of Lightbend, next to their other frameworks such as Lagom and Play framework. And Play and Lagom also use Akka internally. So Akka offers us a single unified programming model for simpler concurrency, distribution, and fault tolerance. What we mean with this is that Akka gives us all these out of the box. So we get these by simply using Akka concurrency because we want to utilize multi-core processors as much as possible. Most of the servers now have access to multiple cores, so we as a developer will need to write code to take advantage of all these cores. We no longer simply program on a single thread model, so yeah, it's up to us now to write our applications and make better use of all the cores that we have available. With distribution, we mean that we can distribute our application over multiple nodes and that the application functions as a whole. And fault tolerance, that's something we will go deeper into in one of the upcoming slides. So more on that in a bit. You will see that with Akka we will make use of the actor model, and the actor model allows us to the actor model is actually an abstraction layer for the developer, and by following this module the developer doesn't need to worry about shared states, threads, synchronized blocks, locks, and all the complex stuff that usually comes with writing a multi-threaded application. So all these are taken care of by Akka for you. And that is one of the major advantages of using Akka. You basically have the illusion of coding a single-threaded application in Akka. But all the code that you are writing is actually, it's all asynchronous, multi-threaded, all being handled for you by Akka. But you have the ease of just writing a single-threaded application. Akka is very good at utilizing the most out of your CPU. And it comes with low latency, high throughput, and scalability, both in horizontal and vertical scaling. So you can add more machines or increase your CPU or RAM, and Akka is able to take advantage of all this. Akka is distributable by design, so it fits the perfect programming model for the cloud. Everything is about the cloud these days, all the cloud hosting platforms. So it's important that we utilize the necessary tools and frameworks that are working well with the cloud. And Akka does this because Akka is elastic, so Akka is able to to adapt to different workload changes. If your workload increase, Akka is able to fit the demand. With self-healing, with a self-healing system, you basically have a system that doesn't go down, but if it encounters a failure, the system just crashes and then recovers from it. So the system is able to perform self-regeneration and to just continue. So you don't really have to call one of the ops guys to tell them that your server is down and that they need to restart it or whatever, or that the memory is full. With Akka, you have a self-healing system. Akka also offers load balancing and cluster rebalancing. And one of the major advantages when using Akka is that the code that you write is distributable by design, as the title says here. And the only thing that you need to do to make use of this is that you have to add a single configuration, a couple of lines to your configuration file, and all the other things is handled for you by Akka. Yeah, this is how Lightbend describes Akka. So with Akka you build powerful, concurrent and distributed applications more easily. That's one of the major points, because writing a multi-threaded application that makes use of all the CPUs that you have available is rather hard if you would go just with plain old vanilla Java. So Akka wants to offer you as a developer an abstraction layer using the actor model to make things easier for you. And he also mentioned here that Akka is a toolkit, so you just plug it in, you just add it as a dependency in your project, and you can start making use of it. So you don't really have to re-architecture your application just to fit the necessary structure that would be demanded by any other framework. And yeah, you use Akka for building highly concurrent, distributed, resilient, message-driven applications on the GVM. So that means that you can make use of Akka both in Scala and Java, and probably any other GVM language that you can think of. So we have it for Java and for Scala. But you might be surprised that there is also a .NET port available, so even the Microsoft guys can make use of Akka. That's wonderful, right? We should tell them. So what are the use cases for Akka? Basically everything on transaction processing, for example, in online gaming, finance or banking, trading, statistics, betting, social media, telecom. You can make use of Akka as a simple service backend that offer web services, for example. You should use Akka if your focus is on high concurrency and parallelism, or also for batch processing. All of these are ideal use cases for Akka. So something more about the actor model that I've been talking about. The actor module is not something new. It has originally been implemented in Erlang in 1986. So it's definitely something of age. It's about 20 years from now. Within the actor model, you have an actor, the actor, which is a primitive unit of computation. And the basic idea of an actor is that you have your actor, and it accepts and responds to messages that you send to it. And depending on the type of message that it receives, it will perform some kind of an action, or it will react to it in one or another way. So we can see right here that we have multiple actors, and what we see is that each actor has his own mailbox, and the mailbox is the queue in which the actor will receive its messages. So here we have a couple of actors sending messages to one another, and all these messages get stocked up inside the mailbox right here. And yeah, what the actor will do is simply respond to these messages that it receives. It's interesting to know that the messages, the order in which they arrive from a certain actor, the order is kept. So you can be sure that yeah, if you have an actor sending 2 messages or 3 messages to another actor, that the order in which the messages were sent is being kept. So for example, if you have one message that depends on the result of the other, you have no worries right there thanks to that. As I just mentioned at the start of this section, an actor is a fundamental unit of computation that, yeah, according to the definition, should embody processing, storage, and communication. The processing in this case is known as a behavior in Akka. So with the behavior, we mean that an actor can change behavior at runtime. For example, you can write your actor to behave differently on messages when a certain trigger has happened. For example, if a limit has been reached, an actor should respond differently to the same message. You can all program that in the actor's behavior. But more on that shortly. We also have storage state. So within each actor that you have, an actor is able to keep its state, and this state, it can mutate, but the state is always kept within the actor. So it's not possible from one actor to influence the state of the other, or to change the state. The state is always kept internally in the actor. And the communication part is obviously the message sending between all the different actors. More about actors. So when you create an actor, you don't necessarily get a reference. You don't get the direct reference to the actor, but what you get instead is an actor reference, which is basically just a pointer towards the actor. And you use this actor reference to send messages to the actor in your code. And the point of this is, for example, when your actor when the actor would encounter a failure or something, an actor has a life cycle, and it can be stopped, it can be restarted, and you don't want that in your code. If you depend on a certain actor, you don't want to have the reference go stale towards the actor. So imagine that your actor encounters a failure and the actor gets stopped or restarted. You don't want to encounter a null pointer at that point. So this is where the actor reference comes in. So basically, behind the scene, the actor is restarted or just restored. But all of this is transparent for the caller. So the caller just keeps his actor reference, and it just keeps sending messages to it. And yeah, it's possible that the sender isn't even aware that the actor is down. So yeah, that's one of the reasons. And also because you don't want to manipulate the actor directly. You just want to send messages to it, and that's it. You don't want to access anything internally of the actor, because that would threaten your code and would break the mindset of being able to make optimally use of a multi-threaded application. So that's just a line you shouldn't pass. So each actor has an ordered mailbox, which is the queue of an actor, in which it stores all the messages that it receives. Something important to note is that all these messages are and should be immutable. So all these messages can have multiple fields, any string, any number, but all these values should be immutable. They shouldn't be able to change once the message has been received by an actor. An actor will always handle one message at a time. So while it may receive multiple messages at the same time, it will always treat one message each time. Last but not least, each actor has a unique address it can be reached on, but more about that in a bit in the next section. As we mentioned at the start, an actor has no shared state. So while it is able to change and mutate its state internally, the state is always kept internal. So it cannot be inspected or retrieved from outside the actor. An actor is able to change behavior at runtime, to react differently on use cases. What is also important to mention here is that so when you create an actor, you basically create you create the actor, but unlike when creating a thread, you don't necessarily reserve a thread immediately when creating an actor. An actor gets a thread assigned in order to process messages, but the thread is only assigned at the moment that the message needs to be treated. And this makes actors very lightweight, and you can create a ton of actors at the startup time of your system, for example, and you have the advantage that it doesn't necessarily need to reserve that many threads for all your actors. So if an actor receives a message, it will enqueue itself on some kind of a dispatcher, and it's the dispatcher that will assign a thread to your actor in order to be able to handle the message. Actors are by nature very lightweight. I believe that a single actor, when created, is only about 400 bytes. So with if you have a gigabyte of RAM, for example, you can create like 2.5 million actors. So this makes the actor system really lightweight and shouldn't hold you back from creating thousands of actors if necessary. About the architecture of an actor. So if you would look at the code of an actor, you will see that there is always a part in which it defines the logic for handling messages. In a different part, you have the definition of the messages itself, and these are always defined as an inner class. And basically, the list of the messages kind of describes the protocol to which your actor responds to. Then, if necessary, you can define a part that contains the different behaviors. Usually, your actor has a single behavior, the default behavior, but it's possible to change the behavior when encountering a certain trigger. Then we have the definition of something called props. Props is basically a blueprint or a reusable recipe of an actor. So I mentioned that when you create an actor, you get an actor reference. Something else to keep in mind is that you never instantiate an actor yourself. So not via the constructor that you would usually do when creating an object in Java. But what you will do instead is you will ask the Akka system to create an actor for you, and you pass the recipe in order to create the actor to it. And this is where the props, this props thingy here comes in. And another advantage is that you can define the props a single time, and that you can reutilize this recipe for creating hundreds or thousands or 10,000s of actors. So you don't always have to You don't always have to go through the constructor. You just reutilize the props, the properties value that you defined. And then it's also possible to make use of any lifecycle event hooks. For example, you have a hook available to have your actor perform something when it's being created or just before it's being deconstructed, or if something happens. These are just methods that you override in your actor. So in all your actors, you extend from a certain actor class that offers you all these methods that you can override. One of the key features of an actor is that it reacts on the messages that it receives. And according to the actor model, an actor is able to react on 4 different ways on messages. When it receives a message, it can send a different message to another actor. It can change its internal state. It can change its behavior. An actor can easily create more actors himself, and this will lead to some kind of an actor hierarchy. So you basically have an actor that can create other actors, and the current actor will become the parent of all the actors. But this we will cover in one of the upcoming slides about the actor hierarchy. This is a simple example of an actor. So what you see right here is we have an Hello World class right here that extends the abstract logging actor class. And this is one of the actor abstract classes that we have available. And this one also offers us a utility method for logging statements. And we see right there that, yeah, at the top you have a static class called hello, and this is one of the messages. This is the definition of one of the messages that the Hello World actor will support. Then we have the constructor, in which you see that we call the receive method, and this receive part right here contains the matching of the logic that needs to be executed when encountering a certain message. And we use the receive builder for this purpose. So you see right here that we perform a match on the hello class, so on the hello message, and we link the on hello method to this message. And afterwards, the build method is invoked from the receive builder. And by writing this code, we basically tell the actor that if it would receive an hello message, it needs to invoke the on hello method, and the hello method is just defined underneath it. So you see that the on hello method, it receives the message that's been sent, and just for this simple use case we just log something that we just log a hello world. But you would typically respond by creating something in the database, for example, or sending a message to a different actor, or any other logic that you can think of. Can you repeat that question, please? Yeah. Yeah, that's true. Yeah, so the question is that the hello message should be known from outside the class. It should be known by the caller that would send the message. And this is correct. It's a best practice to always define the messages that your actor supports as inner classes in your actor class. In this example, we only define the single message, but yeah, you would just enlist multiple static classes in this case, so that when a different actor would want to send a message to this actor, it would just have an overview of all the messages that are being supported, and just out of ease for the developer doing his implementation. So there we had the onHello method, and at the bottom we also have the prop thingy that I mentioned about. So it's also a best practice to define a default props implementation in your actor class. And yeah, so this is the default way. In this props method, you define the default way, the default recipe for constructing an actor of this type. In this example, it's just rather simple. It just creates a new instance of the Hello World class without any parameters. But if you would have a private string, for example, you would pass it also in the props method right here. And in the props method, it would just forward it to the Hello World constructor. This is also an example in Scala. So if you would compare the code required to write this between Scala and Java, you will see that in Scala it's quite a bit more compact and easier to write. Yeah, of course, as Java developers, we know that Java can be a bit verbose. But since Java 8, we have lambdas that ease the pain a bit. But yeah, in Scala, things are even more compact, which makes it nicer to use. I just included this for comparison sake. Yeah. So now we'll do a quick demo. We will just create a basic actor, send a message to it, and then have a look at how we can define a behavior in our actor. Now it just needs to mirror my display for this part. Yep. This should work. Yeah. Okay, so into IntelliJ. Just a quick technical intervention by our tech guy. Meanwhile, I get to take a sip. All right. Boop. So demo time. Just get rid of this. So we will just create a simple class right here. Oops. Oops. So 50 hertz. Unfortunately, our recording camera thing only supports 50 hertz, so we need to change that. Okay. So, demo. A name for an actor. JWorks, for example. I need to change to presentation mode because this is rather small. There. Get rid of this junk. So the first thing that you do when creating an actor is that you extend one of the actor classes. Always extend from the abstract logging actor, but you also have a couple of others. You have an abstract actor that you can make use of, but it's always useful to have logging in an application, right? So just extend from this one. And in the first part of the actor, you should always define the protocol that your actor follows. So we'll just add a comment right here. And we can create, we will just create one of the messages that we will support. So we'll create a static class and we'll call this message. And just to add something extra to the example that we've seen in the presentation, we will pass a piece of text right here. Oops, that's not constructor. So we will define a private string right here to store the text. And we will implement a constructor. Oops, private. Oops. A bit messy, but should be fixed in a minute. Up, like this. Get rid of that. There, that's better. Up. Clean that up. Alright. So in the constructor of our message, we will accept a string. We will just assign it to the variable that we've defined. There. So there's that. So that's the message that we will temporarily just support. And then for the next part, we have the constructor of our actor. So JWorks. For the people watching the stream, JWorks is just the name of our unit. I just couldn't think of anything more meaningful. So, and in the constructor, you have to implement the code necessary to perform the handling of the messages that your actor needs to support. And we do this by implementing the receive method, which is a partial function. A partial function of an object and box unit. I won't go into that, but that's just the signature of the partial function. People familiar with Java 8 will be aware of partial functions. So won't spend any time going into that. If you haven't seen Java 8, you should really look into it because it makes the life as a Java developer a lot better, especially with the lambdas that it introduces since that version. So in the receive method right here, you see that we have to define a partial function of the object boxed unit class right there. And this is done by making use of the receive builder. And this is a builder for the Java implementation that allows you to enlist multiple matches on messages and the methods that it needs to invoke when it encounters the specified type of message. And in here we will support the message class that we just defined. And we will link it to an onMessage method that we will implement right now. Get rid of this. Hop. The parameter type that we receive is an instance of the message. But we should first finish this part right here. So you can specify multiple matches. In this case, we defined a specific match. It's a specific match for the message. Message. Bad naming. I'm good at it. But you also have the possibility to define some kind of a wildcard match using the match any right here. So in here we can just say that if you encounter something else, something else, why not? You can just log something, for example, log info received something else. There. And at the end of all the matches, you have to invoke the build method of your builder. Oops. Like that. So now we can implement the method for reacting to the message. Just out of ease, we will just log something here as well. we'll just say treating message dot 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 there. So now we have our constructor with the matches that it needs to perform. We implemented the method to respond on any messages. For the last part, we just need to define a method for the props thingy. So public static props, and since our what we can also do is just for this demo, we can say that we want some state within our actor, so we can keep track of a counter. So just define a counter right here. It will start at 0, and with this counter we will just keep track of the amount of messages that our actor has received. So anytime the onMessage method is invoked, we will just increment it with 1. Vision has been lost. Help, tech support. Yeah, if I can still be heard on YouTube, we apparently have some technical issues with our projector. But yeah, support is working on it. We can still hear it, but it isn't displaying anything right now. I think that the projector has just shut itself down. Just start it up, perhaps. Yeah, and unfortunately our projector is not self-healing, so we have to call one of our local ops guys to perform a hard reboot. So that noise just woke up the projector. Yeah. Alright. We're back, guys. Everything still working? Yeah. Okay. Let's continue. So, I think so we were in the middle of implementing our JWorks actor right here. And we defined the protocol, the handling of the messages. And we were just about to implement the default recipe for creating our actor. Projector still working, that's good. So you have this props method right here, and you need to return an instance of props, as the signature might tell you. So we'll just use the props create static method right here, and then we have to define the class that the class of the actor for which the recipe needs to be created, together with any parameters that you would add to it, as you can see right here in so we have the class and then a sequence of arguments but in this case we don't have any fields that we need to inject into to pass on to our actors, so we'll just leave it empty. So the class is JWorks, like this. Okay. So, and that's basically it regarding the implementation of our actor. Just because we want to perform a test, we will define a public static void main right here. And the first thing that you need to do is create an instance of an actor system. So this will be the first line of our code right here. Call it system, and you create a system by invoking the create static method of the actor system class. You can give your system a name, which you should always do, because naming things is a good practice. And then we can use the system reference that we received right here to create our actor. So we will call this actor JWorks of the type actor reference, because that's the class that we will receive when creating the actor. And then we use the system and use the actor of method right here. So you can see that the system also offers you other methods for obtaining an actor. You can obtain an actor if you know the address or the path of the actor. But for this example, we just make use of the props that we defined in the actor. So an actor of, and then we need to define the props. We will just pass the props defined in our actor itself. JWorks dot props, like this. And then you should also give your actor a name. So just call it JWorks. And yeah, it's possible to recuperate the actor reference of an actor if you know the name of the actor. That's one of the reasons why you should always name your actors. Know that obtaining an actor reference this way is rather expensive, so it should be evaded as much as possible. No, the projector failed again. Yeah, sorry about that. It's about time that we need to tell our projector guys to upgrade their stuff, because it's yeah, it's not functioning that well. At the end of the presentation, I will link or I will share the address of our company so that you guys can donate for having us buy a different projector. So another hard reboot being performed. The projector is coming to life again. Maybe the projector is overheating, or yeah, whatever. All right, let's continue once more. So we just obtained an actor reference to our actor right here, and now we can just start spamming it with messages. You do this by invoking the tell method of the actor reference. You don't really have that many methods available. If you check all the available methods, but tell is one of them. And you see that in the tell method, it allows you to specify the message object and then an actor reference for passing the sender to it. This is something that you only have to do in Java, because in Scala it's not necessary to pass the sender, but in Scala yeah, you don't have to do this gluing yourself. It will do it automatically for you. But yeah, in Java you just have to do it. So we will create a new message instance. We will just pass it some text. Hi there. Or even better, the projector broke down again. So there's that. And then yeah, you always need to pass an actor reference, and you usually do this by passing the actor reference of the actor that's sending the messages. But in this case, since we are just only getting started, yeah, we're not inside of an actor just yet. So for this purpose, you have a no sender actor reference within the actor reference class, which we will use right here. Yeah, and since we're passing a message, it should be useful if we would add a message to our print statement. So we can just modify it like this, treating message, and we'll just paste it right here. The projector is still online. So, and let's add a couple of more message. We can also log something about the counter that we defined right here. Treating message, and we can we'll just perform a string format, and we will paste our message right here, and we will also add a number right here, like this. So counter message, add a parenthesis here. So, and now we can run our demo. So the projector stays online just long enough for that. And here you see our log statements. So this is the basic logging that you get from extending from the abstract logging actor class right here. You can change this in the properties in the config file of your system. But what you see right here is the log level, a timestamp when the message has been treated, or when the log statement has happened, rather. And then you see the name of the dispatcher that gave the thread to your actor. Here you have the path of your actor, so the address. Yeah. You see our system right here, the actor system, and then you see a user right here. This is something that I will go into back in the presentation, so no need to worry about that right now. And then you see the name of our actor right here. So this is the full address of our actor. And this actor can, this path, this address can be used to obtain an actor reference of our actor right here. And then we have our actual message, or actually log statement, I mean. Yeah, I printed the message like this. Instead, I will just quickly change that up to print out the text. We can just rerun it, because this will appear a bit more, more pretty. And here we have our log statement. So we have our counter that gets incremented each time, an invocation each time a message has been created. And the counter is just to demonstrate the internal state of an actor. And then the text that has been passed down within our message. So this is a basic implementation of an actor. I don't know if there are any questions at this point. No. Okay, then we'll just continue before the projector breaks down again. For the behavior sample, I will just quickly go through a sample I've written before the presentation. because otherwise it would take quite some time. So what we have right here is a different actor. In this use case, we have a door actor, and most people know that doors can be opened and closed. So we will define two different behaviors for our door actor right here. You see the door, the protocol of the door. You can pass it an open message, a close message, and then you can also pass it a pass-through message, because that's what people usually do when they encounter a door. They try to pass through it. So that seemed logical to me. And you know that in the constructor of an actor, you always have to implement the receive method to describe the default behavior of your actor. And actually, for when working with multiple behavior, it's rather simple. Instead of using the receive builder a single time to define the default behavior, you just use it multiple times for each of your behaviors. And you see right here that in the actor class, you define a variable to hold the partial function for your behaviors. So here we defined two variables for our open and closed behavior. And in the constructor, we are implementing the behaviors. So for the open behavior, we code that we want to support the close and pass through message. Whereas for the closed behavior, we only want to support the open and the pass through message. And then for the default behavior, we will link to the closed behavior. Yeah, someone in the audience is asking why we support a pass-through message if the door is closed, but that will be obvious in a bit when I launch the demo. So that's the protocol of our door, and yeah, you can see that you will see that for both behaviors, a different method is used for the pass-through message. But we will just run it because that's more fun. So we see right here that the first message that we send is a pass-through message. Then we will send an open message, another pass-through message, and then a close message. And yeah, this is the reason why we implemented why we specified a method for supporting the pass-through message for a closed door. Yeah, bump. But yeah, that's basically it. What you see in the on open method and the on close method is that the behavior of the actor is changed, and an actor can change its behavior by accessing the become method via the actor's context. So you have a getter available for retrieving the context within your actor, and then you can just call the become method. And then you need to pass it a partial function that describes the behavior of the behavior that the actor needs to obtain. And here we just pass on the closed and the open behavior that we defined above. So yeah, that kind of concludes the demo on behavior. Any questions on that? No? Stupid questions are allowed. Just no questions about the projector, please. Okay. Enough demo for now. Hop. So back to the presentation. For this we will need to change some projector settings. Like this, I believe. I think it's still working. Where's my presentation? There it is. Alright. Next. So the actor hierarchy, something I've mentioned in one of the previous slides. So when working with actors, you have some kind of an hierarchy, just to prevent all the chaotic stuff that could otherwise happen. On the actor hierarchy slide right here, you see that the first actor at the top is the user actor. The user actor is called the user guardian, which is an actor that always exists when creating a new system. So this is kind of the root actor. And starting from that part, when you create a new actor via the system reference, the actors just get linked to it. So for example, here we have two actors, another actor right here and some actor right here who have been instantiated via the system. And then we have a couple of other actors that have been instantiated by the some actor and the other actor right here. And you see that each actor that you see right here always has a parent, and it is the parent actor that will decide on what should happen with the children. Yeah, you always get stuff like the children can never outlive the parent. The parent controls the life cycle of the children actors. And the uses of this will be explained in another different slide that will come up right shortly. So in this part, supervision. Now, when creating an application, the classic way of failure handling is usually the followed. So basically, if you would in your application, you are trying to invoke a service call to a different part of your application, and you do that by accessing the service reference, and then invoking the method. And in the method signature, you see that the service might throw a couple of exceptions, and these are all checked exceptions in Java. So when invoking the method call right there, because it might throw one of the following checked exceptions, you need to implement a way of handling these exceptions. For example, the method that you're trying to invoke might throw an IO exception because it's accessing a file on the file system, and right there you need to implement a way to handle the exception when encountered. And this way of failure handling leads to defensive programming. And what this will lead to is that you have your error handling, your exception handling code mixed all up with your business logic. And yeah, every time you need to call the services method, you always need to handle the same exception probably multiple times the same way. In Akka, this is different. Instead of just handling the failure right there on the spot, what you do is, if an actor encounters a failure of an error, it just escalates it higher up to its parent, and it's there in the parent that you need to define the logic of how it should react to the failure of its child, and it will do so by deciding what needs to happen to the child actor and to its life cycle. So this is where the supervision part comes in. So imagine that at the bottom right we have our child1 actor. The X means that it has just encountered a failure. For example, it tried to access a database, but some way or another the connection to the database broke down, and the actor is now unable to access the database, and it encounters the generic database not found exception, or whatever it might be called. So the child actor will just inform the parent of its failure, and it's then up to the parent, so our some actor guy right here, that needs to decide how it should react to the failure of its child. And yeah, bad parenting is applied right here, and you have access to one of the 4 possible ways of reacting to a failure. You see that, yeah, in the little cloud right there, you see that you have the option to restart, stop, resume, or escalate based on the failure of its child. So this kind of leads to the self-healing characteristics of the actor model in Akka. Basically, yeah, in this case, where the database connection has been lost, a way to handle that would be to just simply restart the actor or just recreate it. And I imagine that when creating the actor in this case, it would receive a connection to the database. So in this case, yeah, just get rid of the actor and just recreate it and give it a new connection to the database. This would solve our problem in this case. But there are other use cases where it would be more useful to completely stop the child, or just ignore the failure and continue, or even to escalate the failure higher up to the parent of our parent actor right here. So just to summarize the supervising part, the child doesn't needs to care about what action it needs to undertake if it would encounter a failure. It's up to the parent to decide what will happen. Kind of the same of parents and children. Yeah. And by following this principle, we have a clear separation of our processing logic and our error handling logic. And this is something that we want to achieve. We don't want to mix the two of those. Yeah, as I mentioned before, we have 4 different ways to influence the actor lifecycle. So you can resume the actor, in which case you kind of ignore the failure that just happens and just tell the actor, yeah, it's okay, just keep on processing messages. And then you have the stop that you can use to shut down the actor. We have a restart to restart the child, optionally together with its state. So you know that an actor is able to keep an inner state. It's possible to persist this state before shutting down the actor. And by doing so, you can recreate the actor and restore its state. So that's one of the options. And finally, you have the rather drastic escalate option right here, to just simply throw the failure higher up the chain to handle. So So the question is whether this state persistence is built into Akka. Akka supports it, that's right. But by default, it isn't active. So you need to implement, or you have to activate it, or just have your actor support persisting its state to the disk, for example. And on startup, it can just be taken and used to recreate the actor. But this is something that we won't cover in this demo. It's something, that should belong in a more advanced presentation on Akka. So to write the logic for your actor to handle the failures of each child is actually done in a strategy section within your actor. So you define a strategy in which you perform, in which you say that, if the actor would encounter this type of exception, it should react in this way. For example, here in the bullet list that I have right here, we say that, if an actor failed to initialize properly, it should just be stopped. Or if the actor could not be killed, just stop it as well. For any default exception, just restart it. Rebooting always works, so why not with actors? And if anything else, any other throwable would be encountered, just escalate it higher up and have the other actor undertake the necessary action. This is an example of a strategy. So we have our supervisor actor right here. It extends the untyped actor. Obviously, they don't want to have any logging support right here. So that's why they extend from the untyped actor. And then we define a variable for our supervisor strategy right here. And then you have the possibility of using one of the strategies that's available. In this case, we have the 1-for-1 strategy. So basically a strategy that is unique for each single actor in your system. It's also possible to define a strategy that should apply to all the actors of all the instances of the actor. But in this case, we just want to define a strategy for each individual in the instance of this actor. And then we have a number, the 10 right here, that should say, yeah, how many times can we encounter a failure before we should undertake any action. And then you have the duration in which the 10 failures should be encountered. So in this case, yeah, if 10 failures are encountered within a minute, undertake this action. And then in this lambda block, we just say that, yeah, okay, if it's an arithmetic exception, oh no, I just explained that a bit wrong. The 10 means, yeah, the amount of times it should handle the exception before, yeah, having the parent go into failure itself. So just to rephrase that one bit, we say that in this strategy, if more than 10 failures are encountered for this current actor instance within a single minute, yeah, the actor will go into failure itself and just have the parent of this actor be informed of its failure. So what we have right here is that if the child actor encounters an arithmetic exception, it should just be ignored. It's all right. In the case of a null pointer exception being thrown by the child, it should be restarted because null pointers are bad. And in any other case, we want to escalate the failure higher up. And finally, you need to pass this strategy implementation in the method supervisor strategy that you need to override. In this case, it's just been written in 2 different parts, but you can obviously just create the strategy right here on the spot. Is this part a bit clear? No? Alright. So next. Ah yeah, and this is the Scala example. Java, Scala. Java, Scala. So yeah, if you like writing compact code, go for Scala. It's that simple. But yeah, Java is still alright. It's a bit verbose, but it's alright. Java, Scala. Next. Now just another quick demo on a custom strategy. I think we can go through it rather quickly. So projector settings. Work with me, please. Damn it. Let's try again. Yeah. Hertz. We need more hertz or less hertz. Where are my hertz? Ah yeah. So hop. No. Optimize. HDMI. So settings. Bear with me, guys. It's going to be all right. And 50 hertz right here. Yes. All right. Demo time, part 2. The projector is still live and kicking. So supervisor part. That's not supervisor part. This is. Oops. So what we have right here is, in this supervising example, we have two actors. We have our supervisor actor right here, which defines a one-for-one strategy. Yes, so one-for-one strategy, and the amount of retries is 10, just as in the presentation. But instead of supporting 10 retries in a minute, we just want to limit ourselves to 10 seconds because we are rather impatient. And then you see that we just defined a simple match on any runtime exception. And in this case, we will restart the child. So, the supervisor, when the supervisor actor, when being created, it will just create a child actor, which is an instance of the unstable actor. We'll just have a look at this actor right here. So in here we have a simple implementation of an actor with a single command message that it supports. And we see here that there is some logic that generates a random integer, and as it's currently written, there is a 90% chance that a runtime exception will be thrown. I'll just lower it a bit just to keep things exciting, like this. Up. And the other remaining part of the actor is not so important. What you see right here is that we implemented, that we overridden a hook, the post-stop hook right here, just to print a log statement to just log when the actor is being stopped. You have quite a lot of hooks available that you can utilize. Just to go over it quickly, we have a hook just before the actor is created, just before it's stopped, restarted, after it's been restarted. So you would use these two for restoring the state of your actor when it's been destroyed and recreated. So there's that. Shoe. Okay. So this is why the actor is called the unstable actor, because from time to time it just throws a runtime exception, which is useful in this use case. And back to the supervisor actor. So when creating the supervisor actor, the supervisor creates its own unstable actor child, and for handling the messages, the supervisor will just pass on any messages it receives to its child. That's about it. So here we have the supervisor strategy that we override, and to which we return the strategy that we defined higher up. So let's just run this demo. So here you see that we will try to send 10 messages to our supervisor unit, and we'll just see how the supervisor will react to it. So we see right here that at the start a new unstable actor is being created by the supervisor, and right from the start things went wrong. So the unstable actor went into unstable mode and threw a runtime exception. And we see that yeah, thanks to the strategy that we put into place, the actor is just being restarted. So here we defined that if any runtime exception would be encountered, yeah, just restart the child actor and let's just try it again. So here we see that the unstable actor child is being stopped. It's being recreated. This is a log statement that I put into the constructor of the unstable child. And here we see that the child actor handled the command well, but then right after it went unstable again. So just restarting again, handling another command, and unstable again. Stopping, creating the child once more. And then it managed to successfully handle 3 commands before going unstable again. But yeah, it's just being recreated. We can, for example, change this right here, and instead of restarting, we can just tell the actor, yeah, just continue, just resume your operations, and don't worry about it. So we'll see what will be the effect of this. And here you see that, yeah, you no longer get to see the exception trace right here, but here instead, yeah, the commands are being handled. Oops, something goes wrong, but let's just ignore it and just continue. So yeah, the actor is just being kept alive, and yeah, it just goes on with business, just like that. Another example would be the stop. And what we see here is that yeah, the actor is being created. It hasn't even managed to treat a single message, but it went right unstable from the bat. And we see that the child is being stopped, and then we see something rather weird, some weird logging statement that I didn't put. But we see here that, yeah, there has been a message, the command message, defined in the unstable actor class, that was sent to command scroll bar, that yeah, has been sent from an actor called dead letters apparently to an instance of unstable actor, so our child, and that the message was not delivered. And yeah, so what this basically means is that any messages that that are being sent but they aren't received by the recipient, all these messages are kept in a dead letters actor's mailbox. And the point of this is to keep track of all the messages that have been lost, and to just store them under the dead letters actor for debugging purposes. For example, it's possible to subscribe to this mailbox and to perform, yeah, to add some extra logging, or for example sending an email to developers to inform them that they wrote a bug or something like that, and that they need to investigate this. But this is just put into place just to keep track of all the messages that are being passed all around. Because yeah, imagine in a system with thousands of actors, you don't want to have any messages disappear. Okay, I think that concludes the supervising demo. Any questions on that? No. Okay. Yeah, there's a question. Yeah. Yeah, that's right. So the question was that for the one-for-one strategy, whether each child is treated individually. That's correct. Yeah, so you have the many-for-one strategy, I believe. Many-for-one. Or the one-for-many, I believe. Uh, let me look into that. So 1-for-1 strategy. There should be a many-to-one strategy, I believe. Well, let's just Google it. Google to the rescue. Many-to-one strategy. Hop. Come on, documentation. Don't let me down. Pop, pop, pom. 1-for-1 strategy. Kinds of strategy. No. All-for-one strategy right here. So we have the all-for-one strategy. Yeah, that's what it's called, the all-for-one strategy. Alright, so we can just try that. So, and with the all-for-one strategy, you basically have the amount of the counter that keeps track of the amount of failures is just being kept together for all the different instances of your actor. So you use the 1-for-1 strategy for treating each actor instance individually, whereas for the all-for-1 strategy, you want to take your decision on the life cycle of the children, like that. Yeah. Yeah. Question is if you can kill them all. Yes, you can. Okay. Back to presentation mode. Yes. Whoop. All right. So then we have the configuration part. So in your Akka system, you have a single application config file in which you can define the necessary settings for logging, routing, remote deployments, dispatchers, 3 topics that we won't cover in this presentation. And then there's also debug settings and many other settings. There is a link on the documentation that contains a really good overview of all the different settings that you can. Come on. Oops. Like this. Hop. So in the documentation of Akka, you have a part that lists all the different settings that you can include in your file, and yeah, I think it's this part. So there are really quite a lot of settings that you can define in here. Like really a lot of them. So yeah, good documentation, always nice. So, and this is a simple application config right here. It uses the Hakon notation. Not sure how you pronounce it, but it's the human optimized config object notation. So it looks a bit like JSON. But yeah, this is the way that you define the config settings in Akka. And just to conclude this presentation, I also created a more complex example of 3 different types of actors and meet the pizza ordering system, actor system. So what we have right here is we have 3 actors. We have an office actor, a developer actor, and a pizza guy actor. And this is basically a system to simulate the way how we at Ordina Belgium JWorks prepare ourselves for an evening workshop. And yeah, we prepare ourselves by just ordering a lot of pizzas to become well fed and try not to fall asleep during the presentation. So what we have right here is we have our office actor that defines three different messages. I know it might be a bit small, but I will just read it out loud. So we have the start workshop message, the knock door message, the receive message, and yeah, that's it. And yeah, in order to start up the workshop simulation, the start workshop message will be sent to the office just by when bootstrapping the system. And it's then up to the office to be a good parent and to delegate all the messages to the developer and the pizza guy for having the developer being able to make his order and to pass on a list of pizzas that the developer wants to order. So this is passed back to the office, and the office in turn will create a pizza guy actor, and it will pass a message that contains a list of the pizzas requested by the developer, and it's then up to the pizza guy to do the necessary work of using dough to make pizza and put them into the oven and finally deliver them back to the office, after which the pizzas can be handed over back to the developer. Yeah, I see that we are running a bit out of time, so I won't go too deep into this example, but I can show you the outcome of this example. So back to changing the projector settings. Bear with me once more. Yeah. Settings. Okay. HDMI. Less hertz. Like this. Up. Back to 50 hertz. I apologize to the guys that have a 144 monitor. Okay. No? Alright. So, for the final demo, pizza orderer. So, we have a workshop runner class right here that will boot up the actor system that we will use right here. And you see that at the start it will create an instance of the office actor. And it will start the process by just sending the office the start workshop message. And yeah, I won't go too deep into detail because it's getting late and people are getting tired. But this is an example that you could try out yourself once you made it safely at home. So let's see the scenario. So here we are starting the workshop. Is it big enough? Yeah, it should be. Okay, so here we are. The office is starting the workshop, and we see a developer, me apparently. So I'm about to make my order of 3 pizzas. Ordering a Hawaiian pizza, a meat lover, and a prosciutto pizza. And we see right here that the office received the order of the 3 pizzas that I ordered right here. I've even printed out the address of my actor, so yeah, my own actor, which I'm very proud of. And then we see that office has made the order and that our pizza guy named Mario right here has received the order of the 3 pizzas, and it needs to be sent at the following address. This is the address that you can also use to donate for a new projector. yeah, we see Mario being a good pizza guy, preparing our 3 pizzas right here. And at the end, yeah, Mario will deliver our pizza order to the address that we enlisted right there. Office is being a good office and paying the pizza guy for all the hard work that he did. And Office accepted the pizzas. Oops. Obviously, Office will inform the developer that the pizzas have arrived, after which Yannick runs vigorously to collect the pizzas, and he starts to eat them all. And then we see that Mario is going to bed because after a hard day of work, Mario is tired. So, and this is a more complex system of 3 actors. So we see our Office actor right here that, yeah, just supports 3 different kinds of messages. And basically, when receiving a message, it will, for one of the messages, when it receives an order, it will create a new actor for an actor of the type pizza guy to take up the order, and it will just send messages to the pizza guy to inform the actor of the things he needs to do. And yeah, once the pizza guy is done with all its work, it will inform Office that it's done. And yeah, when the pizza guy is done with all the hard work, we can see that Office stops the actor. So that's the time when Mario goes to sleep. So in theory, it's all rather simple. It's just basically defining multiple actors and the way on how they should react to one another's messages, and the logic that needs to be executed. That's basically it for the basics of implementing an Akka system. Of course, a more complex topic would be just specifying the right configuration for performing load balancing, or to separate I/O operations from default message handling. You can define multiple dispatchers, each with their own thread pool to assign threads to actors. But yeah, I just wanted to leave that out of this introduction workshop. So one more time, back to the presentation. Any questions about this example, maybe? No. So yeah, this is just to give a small taste of what it's like to, the kind of system that you can implement in Akka. So it's just basically all about message sending in between actors. So what else is there besides a couple of complex subjects? There are also other parts of Akka, for example, Akka cluster, Akka streams, Akka HTTP, and Akka type that are available. So you have multiple dependencies that you can add to your project, and one of the dependencies is just the basics, the core of Akka. But then there are also other dependencies that you can add for Akka for fault-tolerant peer-to-peer based cluster membership services using Akka cluster right here. You have Akka streams for stream processing that you can add to your project. Then you also have Akka HTTP for having an actor-based toolkit for interacting with web services and clients. And the fourth one is a rather interesting one, Akka typed, which is still under development. And you might have noticed that when handling messages, you always need to define the class, but there isn't really any type safety when it comes to handling messages. You can actually send any message that you want to an actor, whether it's a message object, but you can also send it a string or an integer, and the actor won't complain. If it doesn't provide a way to handle that type of message. The message will just go, yeah, it will just ignore the message just like that. It will accept the message, but it won't do anything with it. And in the Akka typed project, we want to add type safety to actors. So with type safety, we mean that when defining the protocol that the actors support, for example, it needs to support 4 different kinds of messages. We want our compiler to inform us when the actor doesn't fulfill the protocol. For example, it only supports 3 out of 4 messages. Yeah, we want to have the compiler inform us that we are missing yeah, the handling code for one of the other messages, but also to avoid the regressions that could be caused when refactoring something in your Akka project. So this is, yeah, a really interesting addition, I must say, because type safety is something very nice. It's something that we as a Java developer really enjoy when the compiler informs us of yeah, a stupid error, stupid typo in our code. So yeah, more type safety is always nice. And then there are also other integrations, other integration supports for Akka. Camel is an example. So you can integrate Camel together with Akka. But yeah, there are a lot of other different supported integrations available. Yeah, I would strongly suggest to try out Akka yourself via the website. The documentation is really nice. They offer a great overview of all the functionalities of Akka, and there are a ton of examples available. For these slides and code samples, I would direct you to the repository that I defined right here under my GitHub profile. And that kind of sums up the basic introduction to Akka. Thanks for watching. Are there still any questions? Yeah, one question. Yeah, that's right. So yeah, definitely. Mm-hmm. Mm-hmm. Yeah, so the question was that is it still worth learning Akka if there are already frameworks that use Akka underneath? The answer would definitely be yes. It would be worth it because Akka still allows you to perform the necessary load balancing and configuring of your Akka system. Um, I know that, for example, with the Lagom framework, the new microservices framework that Lightbend offers. So Lagom uses Akka internally for the message handling and the CQRS and the event sourcing stuff, and for offering asynchronous services. But yeah, the Akka has a default configuration specifically for Lagom that I put into place, but you can play around with this configuration yourself depending on your infrastructure or the services that you have available. But yeah, it's true that one of the advantages of Lagom is that it uses Akka internally, and that you, by using Lagom, you are enjoying the advantages that Akka brings to the table. Yeah, but yeah, it's still worthwhile to have a look at Akka itself, because it allows you to understand how any of the other frameworks work internally. Yeah. Any other questions? Yeah. Mm-hmm. So the question is how the messaging between actors is being done. I believe that so there is the messaging has a really low latency. I believe that it's that the messages happen via TCP, so they are really lightweight. There is a minimal latency. I believe it's a couple of nanoseconds for a message to reach a certain actor. And yeah, that's also one of the advantages of Akka, the really extremely low latency of sending messages. Yeah. Any other questions? Yeah. So the question is whether actors in a distributed environment, whether actors can be can communicate over when the actor is situated in different GVMs. That's right. So you basically have actors, each in a different GVM, possibly communicating with each other, and it remains transparent for the developer. Yeah. So that's also one of the advantages of Akka. It just brings you all that the distributable goodies right out of the box for you. You just have to perform the basic configuration, and that's it. You don't really have to write any other code of how to respond to a message received by an actor in a different GVM or anything like that. Any other questions? No questions from the remaining viewers on our YouTube channel? Okay, so thanks for watching, guys. Have a good evening. Bye.